start. And our speaker today is Georgii Riabov with a talk on constructing of stochastic flows of kernel. By the way, this title reminds me of the title of well-known book, Constructing Non-Homomorphic Stochastic Flow by Darling.
Yes.
So I think it is related, yeah?
Yes.
Okay, please.
But he had a flow of mappings, and I have a flow of kernels.
Okay.
So such stochastic flows, they appear naturally as solutions to stochastic differential equations in the absence of a strong solution. Okay. In my talk, I will consider a locally compact separable metric space M, and P of M will be the space of Borel probability measures in M. By the kernel on M, I will understand a measurable mapping from M to the space of probability measures in M. So E will be the space of all kernels on M equipped with a cylindrical sigma field. When we have a kernel K1 and K2, then we can compose them to get a kernel K2, K1, which acts on the function f as follows. So we first apply K1, then K2.
How this operation is related to measurable structure in the space of the kernels?
It is not measurable, and I will speak about it.
Okay.
So maybe the simplest example of an SDE that doesn't have a strongest solution is the Tanaka SDE. So this is the SDE when dxt is sine xt dbt, b is a Brownian motion. This equation can be formulated in terms of kernels as follows. So we say that K is a solution to the Tanaka SDE if the following expression holds. Okay, so here f is an twice continuously differentiable function, and we can get like one from the Tanaka equation just by using the Ito formula. So we can think that KSTF is the conditional expectation of f of x of t, where we take the expectation over some distribution over solutions of the Tanaka equation.
What does it mean, distribution of solution?
It means that we have some space of solutions to this equation. We have some redistribution on this space, and then we take the expectation.
So do you mean that we have a weak solution like
Yes.
pair Brownian motion and x. And then you do the expectation with respect to initial Brownian motion. Yes.
Yes, with a fixed b.
Yes.
Yes.
Okay.
But for different x's and s's, do you have different Brownian motions?
No, we have one for all.
How for different small x's and
Yes, it was for different small x's.
No, we have one Brownian motion b. We have the initial condition that xs is equal to x.
But let me ask you.
We don't have a strong solution, so we take the expectation.
Okay.
But the distribution of pair is uniquely defined, so you use this.
Exactly.
Yeah, I will show now.
Okay.
What it gives. It holds that all solutions to this equation are in one-to-one correspondence with probability measures on 0, 1 with mean half. And actually, this probability measure, it is the probability that when the solution hits 0, it goes up. Okay, so for this equation, non-uniqueness only appears when the solution hits 0, and then it can goes either by the excursion of b or by the excursion of minus b. Okay, so as another example, we can consider the SD on the circle of this form. So this must be from 1. And in the work of Lejeune and Raymond, it was proved that, well, actually, it was not proved by them that if the sum of k squared ak squared is finite, then we can solve this equation for all initial conditions and get a flow of diffeomorphisms of the circle. But if the sum of k squared, ak squared is infinite, then we cannot do this, but there exists a family of random kernels on the circle such that the following equation holds. And
was this system uniquely defined of kernels? A system of kernels, is it uniquely defined?
Yes.
Thanks.
So these are two examples when we have an SD without a strong solution that leads to a solution in terms of random kernels. And similar results were obtained by Lejeune and Raymond for manifolds. Okay, so in the examples that I show, we have that the solution satisfies the flow property. Also, its distribution depends only on the distribution of KST depends only on T minus S, and on the non-overlapping intervals. Random kernels act independently. Okay, so and this leads to a definition of what is a stochastic flow. Before that, I will give definitions of some spaces. So F is the space of measurable mappings equipped with a cylindrical sigma field. E is the space of kernels also equipped with a cylindrical sigma field. And by a random kernel on M, I will understand a random element in E. Okay, and now this may be the most important question for me in this talk, that the mapping, the composition of kernels is not a measurable mapping. This leads to a number of technical issues. For example, if we have a family KST with stationary independent increments, then it is not clear how to prove the Markov property of a one-point motion. So we define the one-point motion as the expectation of the action of k on some function f. And since we have independent stationary increments and the flow property, it is natural to expect that this will be the transition function. However, because of non-measurability of this mapping, we cannot prove this. Okay, so this this was the reason for introduction of the following notion. Okay, so F is the space of measurable mappings, and probability distribution on F is regular if there exists a measurable mapping J such that for all x, J of phi of x almost surely equals to phi of x. Okay, so then probability distribution on E is called regular if there exists a measurable mapping P, okay, from M times E to the probability measures on M, such that for all x, P of k of x equals to k of x almost surely. And in I believe in 2020, Lejean and Raymond, they gave a definition of stochastic flow of mappings in the following form. So it is a family of random measurable mappings of M, such that the distribution of phi st depends only on t minus s and is regular. And the flow property holds in the following form. Yeah, so here we need to apply the measurable representation to phi st, and then compose it with phi rs to get phi rt. Then we have the independence of increments, and properties number 4 and 5, they are like equivalent to failure condition.
Georgii, an exceptional set.
Depends on RST index.
Okay, thanks. And this J is independent of X. It depends only on what?
On the distribution of IST.
Thanks. Thank you.
Yeah, so they also show that if this holds for one measurable presentation, then it holds for all. Okay. So the definition of stochastic flow of kernels is similar. So it is a family of random elements in E, such that the distribution of KST depends on T minus S and is regular. They define the flow property in the following form. So,
but you told us that composition of kernels is
yes.
The composition, or
this is a composition, but we put here the mapping P. And this actually solves all the issues.
And what is K? Is remind us the definition
Of what?
Presentation of the distribution.
Yeah, it's here.
Georgii, maybe it's good to give us some examples of such representation.
I will give them in the proof. Okay.
Okay.
Okay. So having a flow K, we can define endpoint motions of this flow as follows. So P and T is the transition function that is defined like expectation. So here we take the product of probability measures K0T of xi of the set B. Then Pn is a failure transition function, and these transition functions are consistent in the following sense. So if we pick like k indices from 1 to n, then the image of Pntx under the such projection mapping is pk of pi I1 ik of x. And actually, this is a characterization of stochastic flows. So if we have a sequence of failure transition functions that satisfy this consistency, then one can construct a flow K such that Pn actually defines the finite point motions of the corresponding flow. However, there is a question: what can we say about this this flow K? So, what is its regularity in, let's say, in S and T, and also the presence of this measurable mapping in the definition looks annoying and strange. Okay. Also, a similar result holds for stochastic flows of mappings, but there we need the additional condition that the two-point motion, if it starts from the same from the point like xx, it always must be so both components must be equal. Okay, so in their work, Lejeune and Raymond, they proved that actually a stochastic law of mappings can be constructed in such a way that the action of measurable representation J on phi is equal to phi. And it follows that then we have the equality. But they didn't have this result for kernels, and the reason is that so what they did, they pass from a consistent sequence of transition functions, they pass to coalescing a consistent sequence on measures. And then they have a flow of they have a measure of a valued flow, and from that they obtain the flow K. Okay, so what I want to say is that their construction it didn't allow to get an equality that a measurable representation of K is equal to K. Okay, so and the main point of my talk is to show that it can be obtained. Okay, so this is the result that I want to show. Okay, so we start with a consistent family of failure transition functions. Then one can construct a stochastic flow K such that Pn defines the distribution of endpoint motions. Then all distributions KST actually they share one measurable representation. Moreover, it has a property that P composition P is equal to P. Then we prove that actually P of K is equal to K, and the mapping K is measurable in all variables S, T, X, and omega. And as a result, so we have that in fact KRS KST is equal to KRT. Okay, so now I go to the proof. I will use the following objects. So since M is a locally compact separable metric space, we can write it as a union of compact sets Lk, such that Lk is contained in the interior of Lk plus 1. And we can also construct continuous functions zk, such that zk is equal to 1 on Lk, and the support of zk is contained in the interior of Lk plus 1. Okay, so this is the first lemma, and it will be a lot of lemmas today. Okay, so the first one is a property of failure transition functions. So for any compact in M and for any T, we can find a large compact C2 such that the following inequality holds. Okay, so here this is a probability that we start from X, from C1, and arrive to C2 in time less than T, and this probability is bigger than 1 minus epsilon.
Can we say that this PTX must be continuous as a mapping to the space of probability measures, which is space with respect to Wasserstein distance of zero?
I think so. Yes. Yes.
Then it follows from the statement that if we have
Yes.
compact family, then
Yes.
and Prokhorov theorem, yeah. Okay.
Now, next, let's consider one-point compactification of M. Okay, and the space of probability measures on this compactification. Then, when we start from the consistent sequence Pn, for each n and for each x and t, we can find a probability measure over probability measures on M, which will be the distribution of k of x. To do this, we can introduce the algebra of continuous functions on the space of probability measures on Mn of the following form. Okay, and it is yeah, it must be capital N, and this algebra is dense in the space of continuous functions on probability measures. Okay, and for such function g, we define Pnt x of g as the following integral.
So we think from the beginning was volume of the
Andrei,
I
very
didn't
bad,
hear anything,
very bad hearing of you.
Okay, so maybe let's continue.
Yes, so let's continue.
Yeah, so
then.
this mappings pi n, they are actually linear non-negative functionals on this algebra. And it was proved by Lejeune and Raymond. It means that they can be represented by measures.
Mhm.
So we obtain we obtain the family of probability measures on Pm to the power n, for which the following equality holds. The obtained family is consistent in the following sense. It is coalescing in the following sense. Okay, so these measures are concentrated on P of m, and the mapping P and T x of G is continuous in T and x. Now, as a consequence of this, we can get the following lemma. So by delta epsilon c, I denote the space of the set of measures mu1, mu2, the distance of which is bigger than epsilon. And the next result is that if C is a compact in M, okay, T is less than capital T, then the following limit is 0. So as we saw in the previous result, P2 it has the property which is analogous to the Feller property. So if this is not true, then we can find sequences xk, yk, tk. Okay, xy belongs to the compact C. The distance between x and y is 0, converges to 0, and all these probabilities are bigger than alpha. Okay, then we can estimate this probability by this expectation. And in the limit, because of continuity, we get P2 xx applied to gm, and when m converges to infinity, we get here P2 xx delta epsilon c. But this is impossible, since if the first components are equal, then P2 will live on the diagonal in the space of measures. Now, let Z be an at most countable dense set in M. So the idea is to define the distribution of K0T of Z, and then to recover the distribution of K0T by some limiting procedure. Okay, and to make this limiting procedure, I need the following result, which I talked about maybe last time or two times ago. We can find a measurable mapping in the space of measures such that for any relatively compact sequence mu, L of mu is a limit point of mu. Okay, now we can find a sequence epsilon k such that if t is less than k, xy belongs to compact sets Lk. Yeah, I recall that M is the union of Lk, and they are increasing. And if the distance between x and y is less than epsilon k, then P2xy of delta 2 minus kc will be less than 2 minus k. Now, so Zn is the sum enumeration of Z, and for each point x, we can define indices nxk. So nxk is the first index n, such that the distance between x and Zn is less than epsilon k over 2. And now we can define the following mappings. So the mapping I, it is a mapping of sequences of measures into the space of kernels. So I mu of x, it is the mapping L applied to the sequence mu nxk. In a sense, mu nxk must approximate the distribution of k of x. Okay, so the mapping J is a kind of inverse mapping to I. So J of k gives k of z. And mappings phi n and psi n, they are like compositions of I. Okay, and maybe this is the main point, that the composition of I and J is the identity mapping of on the sequences of measures on M. Because if X is equal to Zm, then for large enough K, we have that Nxk is equal to M. And this sequence of measures mu, it is equal to the one measure mu M. Okay, next, since we have a consistent sequence of probability distributions, we can find for every t a unique probability measure by t whose marginal distributions coincide with pi t of z. And And we have the following result for the measure pi t, that this measure of sequences mu such that the distance between mu xk and mu xk plus 1 is bigger than 2 minus k is less than 2 minus k. And here k small depends only on the compact k in M, and is independent on everything else, I think. Okay, for all large enough k, we have that the distance between z and xk and x is less than epsilon chi over 2. The distance between z and xk plus 1 and x is less than epsilon k plus 1 over 2. And also, we can take k as large so that t is less than k, and z n xk and z n xk plus 1 belongs to Lk. Okay, and now since the distance between z n xk and z n xk plus 1 is less than epsilon k, we obtain that this probability, which is equal to this one, is less than 2 minus k. Okay, the next lemma is that for almost all sequences mu under the probability pi t, the limit of mu and xk is equal to I mu of x. This is because we have an estimate which holds for large enough k. So it means that the distance between mu and xk and mu and xk plus 1, they form a convergent series. It means that there exists a limit of mu and xk. But I mu is a limit point of mu. Okay. Also, we can estimate the distance between mu and xk and I mu of x. If k is a compact in M, then uniformly for all x in k, for all large enough k, we have an estimate. Yeah, so here I show how to obtain it. Okay, then one more lemma. If we have a compact in M, then the mapping I is in a sense continuous in probability on K. And, one more lemma. If if X is a sequence in M and Y is an independent sequence in the space of measures on M, if the distribution of Y is pi t, and if xn converges to X, then Iy of xn converges to Iy of X. Yeah, but this is basically the result of Lejeune and Riemann. Okay, so now let's define the distribution of K. It is the image of pi t under the mapping I. It is a regular probability measure on the space E, and its measurable representation is equally actually I composition of J. Because the measure nu ut such that pk of x equal to k of x, it is the same as ut. The measure ut is such that I of j of k of x equal to k of x, and we define ut as the image of pi t. So this is the measure pi t of mu such that I of j of I of mu is equal to I of mu. Okay, but this is the identity on the space of sequences of measures. So we get 1. Next, if we take a continuous function on the space of measures, then the integral of this continuous function of kx1, kxn is equal to pnt of f. Yeah, so here g must be in the form like integral of over mn f of y mu1 mu n dy. Okay, and since we proved convergence of y and kx1, y and kxn, and so on, get this equality. So what we obtain a regular distribution on the space of kernels on n, and we find the same measurable representation of all these distributions nu t, and it has the property that p composition p is equal to p. So I recall that p is I composition j, so p composition p is I composition j composition I composition j, which is equal to I composition j. Okay, so in fact, what I do next is the repetition of the work of Lejeune and Riemann. The difference is that I can work in the space of measures, and the measurable representation is the same for all measures and idempotent. All the next basically follows the construction of Lejeune and Raymond. So we have a sequence of probability spaces. Here, omega n will be the distribution of the kernel k that acts from L2 minus n to L plus 1 to 2 minus n. We have the following projection mappings that are measurable, surjective, and the probability measure Pn under the mapping Pn minus 1n is equal to the measure Pn minus 1n. Then we can consider the inverse limit of these spaces with the natural sigma field A, and by the well-known result on A, we can find a unique probability measure whose projections under pi n is equal to Pn. Okay, so here are some sigma fields. We'll show a number of lemmas. Okay, so if intervals Rs and St are disjoint, then the corresponding sigma fields are independent, and then we can define a number of measurable mappings on the constructed probability space. So first, Kn, it's like an approximation of the flow from S to T. Here, like the segment St is divided into 2 to the n parts, and we take the mappings omega between them, and then compose them by our measurable composition. Okay, then KST, if S is less than T, then KST is defined as the measurable representation of Kn. Okay. And maybe this will be the last slide. To get the flow K, we first approximate ST by the rational approximations SKTK, and take a limit point of them. And then it remains to apply the presentation P to K prime to get the flow K. And now it is obvious that P of K is equal to K. I think this is what I wanted to talk. If
Okay. Thank you very much for interesting talk. And maybe somebody have questions or comments, please. No. Andrei, again trying to say something, yeah?
Georgi, so do I understand correct that you used two properties? The first, you have some approximation by measurable mappings or that you can construct, and then Fowler property. And you prove, okay, and you use that the limit of measure, if you have a sequence of measurable mappings that depends on certain parameter, and assume that, so this parameter is measure or a point. And then you prove that for each fixed point or measure, you have a limit in probability. Then you can select measurable, then you can select a version of a limit, which is measurable omega times this parameter.
Yes, yes.
And then you apply Fowler property and you apply Fowler property to prove that composition, you can consider that the limit of compositions is a composition of limit. Is that correct or no?
As I understand, it is almost surely, yes, holds.
Yes,
Yes.
yes. So
Yes.
this was idea that
Yes.
you have independence, you have Fowler property and measurability of pre-limit processes, and the question was how to pass to a limit, and you prove that the same property for compositions holds because you have independence plus Fowler property.
Yes.
Thank you.
Okay, Georgi. So still we have no any examples, yeah? But let me ask you the following. In the case of usual stochastic flow, we have some interesting property in random points. We have, for example, we have two trajectories which came into the point and two trajectories which came out the point. What can be analog of such property for flow of kernels?
Well, if we have a flow, we have a point, then the idea is that the mass from this point can like diffuse.
Yes, but why not? It can diffuse in two different ways, yeah? Or several different ways.
Yeah.
Yeah, so this will be like formal analog of those properties that we have some very special double point in, for example, in a radial flow. Now you have the flow of kernels, so you have a good superposition property at any fixed deterministic moment of the time. But what happened in random moments of the time? Maybe there are some such singularities.
I'm sure
Bifurcation points.
Yes.
What can be bifurcation point now?
Well, I have to think about this because.
Okay, because it looks that construction is almost finished, so you can now consider different examples like related to Tanaka equation, not only on the real line but on refs and so on. But it is interesting what we will have when we try to find, for example, what is the backward flow, yeah, and so on. So remains a lot of work here besides of this formal construction.
Georgi, and for Tanaka flow of kernels, do you have some strong existence and uniqueness?
In what sense?
So so for Tanaka equation, there is no strong existence. But is there a notion like strong existence or strong uniqueness for flow of kernels?
Yeah, but I showed in the beginning.
Because I think because of uniqueness of weak solution. Yeah.
I showed that all solutions to equation 1, they are in one-to-one correspondence with the probability measures.
Mm. And by the way, let me comment on this Tanaka equation. I proposed that maybe in 2004 or 5 the idea of measure-valued solution, random measure-valued solution to stochastic differential equation when there are no strong solution. It was like conditional distribution of the weak solution with respect to
Exactly.
Brownian noise. Yeah. Oh, now something happened with the internet. So, I think it is very related. Yes.
I think that this is exactly what it is. So this is exactly
Yeah. Yes.
the solution K.
Mm. Okay. Okay. Thank you again for the talk. Hope to see valued examples of such flows and their interesting properties in the future. And who will be the next speaker next week?
It will be your joint talk with Novafil.
Oh, okay. So maybe not. I hope. I will ask him. Okay. So then see you next week. Bye.
Goodbye.
Thank you. Bye.